Yeah, I'm back. Yeah. All day with the necessary, I guess. Great.
We're starting 5 minutes late because they're in line for coffee.
That's the end.
Executive decision by the chair.
Thank you, Steve. Thanks very much for inviting me. I'm first time in Stockholm and enjoy myself a great deal, except that I'm still feeling a little sick. That's why I had to postpone my trip here. It's not completely over, but I decided that it's good enough for, not for you, but it's good enough for giving a talk. So I first like to thank my two collaborators. Maurizio Stone is a PhD student who will finish within the next 6 weeks or so, and Sankara Sama, whom all of you probably know. I'm very grateful, especially to Bert Halperin, who has guided me through many of these studies. Nick Brumenil, who has been always very critical, and Jörg Fröhlich was very interested, which is something that I think is also extremely useful if you have competent people who show interest. In earlier times, you may know that I wrote the paper about 10 years ago. It was Horst Stürmer that kept me going. He would ask me again and again, how is it going? Do you still believe it's this? And I said, yes, I still believe, although I can't really justify it in a way that everybody will buy. I still can't do that. As you will see, not everybody will buy. The main things that I am showing buy in the sense of how much importance one gives those observations. That's the question. When I say reasons to be hopeful, I mean new physics is something that we all like to see. And when I say reasons to be hopeful, I want to communicate the idea that we do not have observations that make us very wary about whether these new physics can happen or not. And of course, the new physics is not so new, but it may be new that it is realized in nature, is the non-abelian statistics of excitations in fractional quantum Hall states. So that is what I mean by reasons to be hopeful, and I will try to explain those observations that I call reasons to be hopeful. So, since many people are new to this field, I should remind you that the question of polarization, spin polarization of the 5-half state, is by no means settled at this point. Experimenters are not sure that it is a polarized state. The main results that tell us that it is most likely a polarized state are numerical, not experimental. And there have been recently new experiments by Guillaume Gervais that have perhaps also made us aware that the polarization issue is not all that clear, and there are attempts now, especially by Aaron Pinsock, to do light scattering experiments and try to establish the polarization, to study the polarization question in the experimental system. So I start with what's known about spin polarization based on old results that are in the literature. I'll tell you something about the shift on the sphere, which is I would say, a characteristic of quantum Hall states, and you'll see that this can tell us something interesting. The new results concern now the question whether we have a reason to believe that the Coulomb ground state in actual experimental system, it has the nature of the Moore-Reed-Pfaffian. I'm emphasizing it's the Coulomb ground state that we investigate. We don't, at this point, investigate, at this point, that's line number 3, at this point, investigate excitations. But I will then also show you that the phase which is gapped in a domain of characterized by Haldane pseudopotentials matches the phase with big overlap between ground state and the Pfaffian, which is quite interesting. Then I will show you excitations, discuss briefly how to localize quasi-poles, how do they look, what they look like, how big they are, what their shape is. And then I will show you some new results that display adiabatic continuity between the Coulomb ground state of two-hole system, two quasi-hole system in a U equals 5-half state between the ground state and the Moore-Reed-Pfaffian of two quasi-holes. And then I will show you some, I would call it preliminary evidence, but for grading, maybe let's call it preliminary evidence for grading, because this is something that might become more interesting as our technique for studying such systems is further developed. I'll end with conclusions and open problems. So let's dive right into the old results. At this point, we studied both spin polarized, fully polarized or fully unpolarized systems. And that's all work that I have published about 10 years ago that everyone can look up. But I want to remind you that this is basically the only evidence we have so far well, it's not the only one by now. So there have been, I'll mention briefly, other work that has studied the spin polarization question at 5.5. But when I published this paper, this was the only evidence that quantized state may be polarized. Now I should remind you why this has been somehow a surprise. The surprise was that everybody kind of had assumed that the quantized state is a spin singlet, and that the Zeeman energy, when you tilt the sample and increase the Zeeman energy, that it was the Zeeman energy that was responsible in eliminating the quantized Hall plateau in a tilted field. That was the generally accepted scenario. If the system is polarized already in the perpendicular case without tilting, you will, of course, cannot expect a transition in spin polarization. It remains polarized in a tilted field. The Zeeman energy will increase, and therefore there is not going to be a spin transition. If there is no spin transition, well, why does the plateau disappear? So it was an almost universally accepted scenario that the quantized state is a singlet which becomes unstable when the Zeeman field is too big. That was generally accepted. Now, for about 10 years, I tried to find the unpolarized state that is responsible and couldn't find it. So I'm not talking much about shift now. This is an unbiased study of systems. The top is unpolarized, the middle is polarized, and the third panel is the difference between polarized and unpolarized for certain shift. I might remind you, the shift is the number 4, 2, 5, 3, 1, etc. That is missing in the. If we were on the torus, the shift would always be 0 on the sphere. It's characteristic of quantum Hall states. I mentioned that in the beginning. But here I do a completely unbiased search for states that might have properties of a quantized state.
So how do you fix polarization when you do your calculations?
How do I fix polarization? I actually use decomposition in terms of products of basis states that will have singlet symmetry or fully antisymmetrized wave functions. To actually generate the ones with singlet symmetry, you have to satisfy those cyclic Fock conditions, and it's not easy to go to big systems. These are 12 electrons in the singlet state, but that's a very old calculation. Those were done in 1994. It took me many years to actually come out with this paper, because I wanted to have a scenario that explains why the quantized Hall state disappears, even though it is a polarized state. That was the missing link. Unless I have a scenario, it's all dangling in the air. Unless you have a scenario why the state might disappear. That was the thing why I had to wait so long. I didn't know what was happening. So those were quite old results. 12 electrons. That was done on a DEC workstation. Anyhow, so what we see here is there are very strong finite size corrections, and only the ones with even shift have ground states, can have ground states with L equals 0, which we require for quantized state. If we look here at the difference, there is one state at 6 electrons that's very low in energy. This is the difference between the unpolarized and the polarized state with exactly the same quantum numbers. And we can ask the question, well, what's typically happening? Typically, the polarized state is lower in energy. But here is an example where the polarized state is higher in energy at 0 Zeeman energy. That's zero Zeeman energy.
Actually, if I may comment on that one.
Right.
Actually, that state of n equals 8, I believe, is the highest with a
Unlimited.
series. I think that state of n equals 8 for a series of 2n minus 3 is the highest actually with a it's 2/3 states.
It's not this one. It's not this one. This one is a 2n minus. It's a 2n minus 2.
Right, but it's also in the series of 3
Oh!
n plus 1.
Yes, actually, I pointed out that in my paper, in this old paper, that it matched a 2/3 singlet state. It's a 2/3 singlet state. But I actually don't think it's it's more likely a phase-separated state. But you're right. Actually I wrote about that. That was pointed out. But for a long time I didn't know what it stood for. It's aliased, as you say. It's aliased with the 3/2 state, with the 2/3 state, with the 3/2 n plus 1. And this is the only one. And of course I was thinking that perhaps this would turn up again at 12, because you could imagine that you need clusters of 6 to be able to produce such states. And that's why I went through all the I did some tremendous effort to use all symmetries and to use other tricks to go up to larger systems, just to discover that these unpolarized states are polarized states in disguise. They are really polarized states on which you, by demanding that they be singlet, they nucleate a large wavelength, long wavelength spin structure, something like a skyrmion. So I don't want to read this all for you. The bottom line is the quantized state is most likely spin polarized, otherwise we see no gap. And if we look at the polarized system, we find that only shift 3 gives L equals 0 states for all even sizes that we can observe. Up to this point I was looking up to n equals 16, I believe, in this old paper. Now we know it up to 20. We know it up to 20 electrons. And we could actually go a little beyond that. For other shift, interesting, that is something that I also pointed out 10 years ago, that the lowest energy excitations show L equals 0 or 1 or 2 when you deviate from shift 3, shift 1 for example, or shift 2. Shift 2 would be consistent with the 2 quasi-pole excitation in this system, with 2 quasi-holes separated by fairly large distance, as it's possible on the sphere. And it's either L equals 1 or L equals 0, which depends on the lowest energy state, which depends on whether n is divisible by 4 or only by 2. So it's some kind of an even-odd effect. There are recent papers on the question of spin polarization. I know 2 which confirm the this bottom line, that most likely the quantized state at 5½ is spin polarized, but experimentally we don't know. And we should be aware, experimentally we don't know. So it's... However, there are experiments that I will quickly comment on. Yes?
So experimentally, for many other fractions, you can have fully spin polarized as well as partially spin polarized as well as spin singlet states.
Right.
So here also there is a possibility, experimentally, that at high magnetic fields the state is fully polarized, but it may not be fully polarized.
We don't know. Maybe I briefly review also what was known at the time concerning when we vary the Haldane pseudopotentials. When we vary V1, V1 is the one that is most active. It really makes the difference between lowest Landau level physics and second Landau level physics. In the second Landau level, V1 is very much smaller than in the lowest Landau level. And many features that we observe in the second Landau level, which are absent in the lowest Landau level, are resulting from this change of V1. Actually, there is also a change of V2. V2 is increased in the second Landau level compared to the lowest Landau level. And that is an important observation, because the question of spin mixing is directly is a direct consequence of the change of V2. Maybe I have time to get back to that. So let me summarize those results. This is an 8-electron spectrum. This is a 16-electron spectrum, and in both cases we see a window in which L equals 0 is the ground state with a gap of the order of 0.02. Here also 0.02 or 0.03 maximum gap to the lowest energy excitations. We wouldn't call that the intrinsic gap. The intrinsic gap would be the one when the neutral excitation is too large separation, when the quasi-whole, quasi-particle forming it are at infinite distance. But these would be finite system gaps. We see here in both cases that there is a window in which the ground state is L equals 0. And here I show the overlap with the Pfaffian, but I also show the overlap with the pair wave function that was done in that paper, especially not to tell people that we have a better wave function, but to tell people that we can't discriminate. That means I should not be quoted as having said the ground state has Pfaffian nature. We don't know. It may or may not. The reason why I'm here is that we have gone on with this question, and I'll show you new results on that. Here we show again the overlap, not with the Pfaffian, but with a putative pair wave function, pair state.
Is the pair wave function in the same phase of matter as the Pfaffian?
It should not be. Bert's argument had been that it should be 8-fold degenerate on the torus. But we don't exactly know whether after anti-symmetrization it might not actually be in the same universality class. We don't know for sure. The problem, as with many trial wave functions, if you don't know the Hamiltonian for which they are exact, there is little that you can do that is really solid. And that's not
true, but anyway.
Maybe we can postpone the discussion on these matters.
Let's postpone.
Is it easy to write down what this pair wave function is?
Yes, I have written it down. I will show it to you at the end. I have used up 20 minutes. We started at 5:35 and it's 5 5 to 11, and I'm
What happens if n equals 18 particles? Is there an n equals 0 by, like odd even effect, 2 times odd, 2 times even effect? What happens to the
you
n
will
equals
see
0?
that in a moment. These are the old results. I don't have n equals 18 here. Not yet. This is n equals 16. Did you think this was 18?
No.
Oh,
I was asking what the...
Okay, but
2 times even.
the one thing I didn't mention is that as we go to large V1, we cross over into this composite fermion liquid state. This is a composite fermion wave function overlap. Of course, that occurs for a different value of the flux on the sphere, but I have listed it in the same graph. So the scenario would be the paired state is stable in a window, gap of the order of 0.025. Gap is maximum when V1 has a value such that the overlap with the Gaussian or with the pair wave function is maximum. That's quite interesting. And we'll see that this is a feature that will become obvious in what I'm going to show you concerning new results. Now here, this question, what happens when we go to V1 less than 0.9? That conclusion I do not make now anymore. These were the old conclusions. This is the old work. But now of course I tell you now what is missing in the old work. What's missing in the old work is the question, have we any reason to be hopeful?
What is the state at V1 equals 1?
V1 equals 1.
Are you sure it's not
V1 equals 1
term
is a
density?
Coulomb ground state where the gap is big, but it's not maximum. It is maximum at something like 5% above V1. Does that answer your question?
Yeah, but you can for sure say that it's not a term
It's
density.
definitely a quantized state at V1 equals 1. I don't need... Okay, now, there is one experiment, I alluded to that a while ago, one experiment that I really think we can take more seriously than people are now taking it. The reason why this paper has been criticized a great deal, but not because of the results. It has been criticized because of the arguments that were given to interpret the results. I'm not telling you the wrong arguments because you can check that. I think that I'm not sure if it's still in this version. In the original archive, the wrong arguments are there. But in the published version in solid state communication, I'm not sure that they are still there because I think Sankara Sama pointed out what's wrong about the arguments. Now, I think, although there have been wrong arguments, the paper is still telling us something very interesting. What's happened here? We look at the system in a large range of magnetic fields, and this is not a result of tilt, but it's the result of having a variable density sample. This is a sample in which one varies the density by something like a factor of 2. It's about from 0.5 to 11. It's about a factor of 2, a little more than a factor of 2. And what is interesting is that the gap seems to be a smooth function. Suppose the ground state undergoes a transition from unpolarized to polarized. It would be a miracle if the gap in both cases was the same. To have a continuous gap function, of course it might be the result of bad analysis or of a biased analysis, but I doubt it. Pan is a careful person, and I did discuss this with my Pan. So the fact that the gap is a smooth function, I think, implies two things. First, implies that there is no spin transition occurring in the ground state, because if there was, we would expect a break in slope, or we would a discontinuity in the gap. If the spin state of the excitations was changing, we might expect a change in slope, like at 8/5. That was the comparison. 8/5 shows a spin transition from singlet at low fields to polarized at high fields. And there, actually, it's not so clear that the gap matches. Later experiments by Jim Eisenstein have allowed a discontinuity when it changes, but the slope goes from positive to negative, or from negative to positive, depending on how we look at it. And that would be consistent with the lowest excitation being spin reversed from a singlet. Spin reversed from a singlet means you flip the excited state spin into the good direction, and you gain Zeeman energy by increasing the field. The gain in Zeeman energy increases, and thereby the gap gets smaller, and vice versa in the high field regime. So the absence of discontinuity and break in slope, I think, is something we must at least acknowledge. How much we derive from this, how much faith we have in conclusions, that's another matter. But I take it seriously. So now I come to the new results. These new results are there to try and study the question whether we have right to expect some justification to expect new physics in this system. And I have to add this following when. I actually hadn't realized that Wen had done something very similar many years ago. He told me when I met him at MIT that he had done something similar, and I was very embarrassed that I hadn't read the whole of the paper, because I had studied the edge properties. It was an investigation of edge properties of the Parthian in the disk geometry. But he had actually also looked at the question what happens as we go from a pure two-body interaction to the three-body interaction, for which the Parthian is the exact zero energy ground state. What he did not do is he didn't have Coulomb here. He called it the V1, V3 model. He was just varying V1 and V3 to get into a phase where the overlap with the Parthian was finite. And whether the Coulomb in the lowest or second Landau level would satisfy these conditions was not known then. And most people didn't pay too much attention, because in 1992 everybody believed that it was a singlet state that was responsible for the, not everybody, but many people believed it was singlet, because one didn't have any idea what it could be otherwise. And so the three-body interaction, everybody knows, the SIKM is just a symmetrizer that symmetrizes between IK and M. And the scaling factor in front makes sure that the energy in a system of n electrons grows, is an extensive quantity. It takes care of all the derivatives and the delta functions, so that the energy scales as n. Here I show you the expectation value of V3 over n as a function of 1 over n in the in a filled Landau level. In a filled Landau level, of course, you have to be bigger than half, otherwise the energy is zero. In a filled Landau level, of course, it's very trivial to evaluate this three-body interaction. That's the way. These are curvature effects that we see on the sphere, that there is a 1 over n and a smaller 1 over n square correction in the energy per particle versus 1 over n. That's typical. We would see similar things for Coulomb interaction as well. But I listed this just to demonstrate that you have to use a proper scaling for which the energy is extensive. And for this extensive energy, the gap of V3 alone, no Coulomb, just V3, is finite in the thermodynamic limit. We have also evaluated that. We have calculated the gap at 5½ in a half-filled lambda with V3 alone. And we can now use a scale parameter, lambda, which is system size independent, which fixes the gap at x equals 1 to be the same as the Coulomb gap at x equals 0. It's very important. Lambda is not varying with system size. Lambda is a constant. The system size dependence is over here, which makes sure that the energy is extensive in a phase where the energy is finite. Because as we know, for strictly nu equals 5½ the energy will be 0 for x equals 1. So that's very important, because if we had a lambda that we were able to adjust with system size so that the gaps would always match, we could also get adiabatic continuity between critical states and, of course, a critical state, if we look always at finite systems, it always has a finite gap. But if we have to blow up the gap to get always the same gap as the Coulomb interaction, then of course we work with energies that are no longer extensive. They would grow faster with system size than n. Okay, so that is the model that we study. So we study now what happens to ground state if we vary x.
So do you have results for gaps just for the V3 body?
Yes, I have them. Yes, I have them, but I don't have a slide of them, but I have them. If you're interested, I can give them to you. They have less size dependence than the Coulomb gap. It's less size dependent. Coulomb gaps, you will see in a moment. Of course, we are interested in the Coulomb gaps for the question of experiment. We like to know what are the intrinsic gaps, because that tells us something about at what temperatures we might be able to perform all these fancy quantum bit operations. So, here I show you one after the other. This is 10 electrons, 12 electrons. The ground state is the reference zero energy. And lambda is never changed again. It's set for, you will see for large systems that the gap at x equals 0 and the gap at x equals 1 will match. For small systems it is not exactly the case. Here it's not exactly the case, but for large systems. Here we see the overlap. That's the overlap of the Parthian with the Coulomb ground state. This is the overlap of the Coulomb ground state with the x-dependent. Of course, at the end points they are the same, but in between. There is a reason why I display both. You'll see later. So what we see here at 10 and 12 is it seems that the gap has a maximum in between, not at neither at 1 nor at 0 in between. And this is the same at 14, at 16. Now you see the gaps are very, very close to the same. And the same at 18. At 18 we don't have all these excited states because, well, we could have done it, but I did this calculation about 5 or 6 months ago, and when I say I did it, I could just as well say we did it because we were both working on this, Mauricio Sony and I. It was truly joint work. And here you see that the overlap is not very big, but the gap does not have any tendency, doesn't signal us any kind of instability. We don't have to expect from these results any kind of instability in between x equals 1 and x equals 0. X equals 0, I remind you, is Coulomb ground state. X equals 1 is the Parthian at this size, 16, and what people will immediately see is that the excited states cross and they do all kinds of funny things, and let's see what happens at nu equals a third. Of course, we knew from Duncan Haldane and Ed Rezai's work of 1985 that when you go from this x here is an x that distinguishes between Coulomb and pure V1 state. As we go to V1 to x equals infinity, this state will be a pure Laughlin state. It's scaled in such a way that the gap goes to a finite value, so it's not V1 itself that we modify, but we modify the 1 over x times the Coulomb plus V1. So it's not that we switch off Coulomb and keep V1 equals 1, or V1 equals the Coulomb value. So in this graph, of course, the graph that everybody has seen in Duncan Haldane is one where the gap just linearly increases with x. But this x is one that measures the relative importance of the Coulomb contributions. Is there a problem? You seem to be
Well, I just
skeptical
wondered-
about this?
Well, I just wondered why you would introduce
I
such
did
an
it.
X that
Well, I did it because I wanted to have something that
compares to.
yeah, but you see, there is a very big difference in the Laughlin case. In the Laughlin case, the wave function is asymptotically exact, whereas we saw that the Parthian is a good representation, or possibly a good representation in a window, not asymptotically. And so if I want to compare things in this manner, I chose this representation of the 1/3 picture.
Maybe a question about the result at 5/2. So this is the pure Coulomb interaction in second order. You don't tweak the V1 to get the maximum overlap, right?
No.
This is really the pure Coulomb.
Yes, absolutely. There's no fudging, nothing, just Coulomb, straight Coulomb, Coulomb interaction of point particles. No tuning, none at all. Thank you for this question. So, that was something that I had actually put together before these questions of Gaussian and adiabatic continuity, etc., were discussed. I had that right in my original. We had it right in our original work. Adiabatic continuity can be misleading in a finite system. I think it cannot be misleading if we are able to establish it for the thermodynamic limit, but no one expects this to be possible with numerical calculations. We might just get an idea whether this may be so or may be not so. If we had seen indications that the phase transition might occur as a function of x, as we vary the interaction, we might have become wary. We'd have to be extra cautious. But we haven't seen that. But now I'm telling you, there is also another way that we can be misled. Here, we knew that the Pfaffian on the sphere occurs for quantum numbers for which you can also see a hierarchy state. And this is precisely the case when n equals 12 in the Pfaffian, or 10 at 2/5. 10 at 2/5 is a hole system of 12 holes. The 12-hole system is the particle-hole conjugate to this system. And if we vary x, we would expect to go from a Pfaffian to a hierarchy state, because the hierarchy state is the one that's established for Coulomb interaction. So let's see what this looks like. In the second Landau level, it looks exactly the same as what we saw for n equals 10, 14, 16, 18. It looks exactly the same. It has a maximum roughly in the middle, gap maximum roughly in the middle, or maybe it's here. But the gap maximum is definitely, there is no hint that there's any kind of transition. Also, when we look at the overlap, there is no, it looks entirely normal. However, if we look at it in the lowest Landau level, there is a tremendous change occurring. We have a gap. We happen to have a gap. The ground state is continuous, and the gap is steadily increasing. But at the same time, we see a relatively fast drop in the overlap. And if we ask the question, what is the maximum overlap of the Pfaffian wave function with which L equals 0 state over here for the Coulomb interaction in the lowest Landau level, maybe this is 5/2, this is 1/2. So at 1/2, V1 is different, V3 is different. It favors Pfaffian over here, it favors hierarchy over here. But we are able to continuously connect the two, which I'm repeating is the misleading aspect of this adiabatic continuity. So if we ask the question, what's the maximum overlap of this state with the with states over here, then we find it's a state which happens at energy 0.128, up here, about up here. That's where the ground state, the Pfaffian, has the biggest overlap. So it doesn't have a big overlap with the ground state over here, but it has a very big overlap with an excited state. So that's how it's misleading if you just look at the system size. As Jacques Nguyen did, he did it for 10 electrons. I am claiming that this is evidence, but it is in no way conclusive. In no way, not at all. Because before we know whether the system size dependence is indicating dangerous development, we don't know anything. So here, of course, this property will never repeat. This aliasing occurs for 10 and 12 electrons, for 12 electrons and 10 and 12 holes. This happens once for all system sizes only. It's exactly once that this happens, and to see that evidence is completely misleading. So one has to be careful. So now I'm showing you what I alluded to. This is the phase diagram in V1, V3 plane at n equals 16. Those are the gaps in V1, V3, and V1 equals 1. 1 is the Coulomb point somewhere here. And this is the overlap with the Pfaffian. Now you see two things. First, there is this regime of non-quantized. There's no quantized regime with not L equals 0 ground state. Ground state occurs at some variable L, that is gapless phase. And as soon as there is a minor gap occurring, the overlap jumps. The overlap doesn't go gradually to 0, but it jumps. In other words, where the gap is finite, the overlap is fairly substantial, whatever, however we want to consider. The observation that the gap maximum occurs at the V1 value where the overlap is maximum is now, that I mentioned before, is now a property in a two-dimensional phase diagram where V1 and V3 are varied. Those are the most important pseudopotentials. The V1 and V3 are the ones that are really also the ones that are modified, for example, by finite thickness and by, of course, there are. Maybe I shouldn't bring up that subject. But in a tilted field, some other interesting effects occur that I have no time to discuss at this point. There is another question. What happens over here? This is a question that I'm not going to address today, but if people are interested, I'm ready to tell you about results concerning possible other phase, which is not a Parthian phase, but another kind of quantized phase. And we at S equals 3, shift 3, we don't observe the ground state, we observe a state with excitations present, with charged excitations present. So the message to take home is, when we want to characterize the gap phase, we can just as well characterize it by overlap with a model state that we had known from the work of Reed and Moore, among others. Here I show you something that is also quite interesting. With the blue and the red trajectories stand for the V1, V3 values that we can realize in the lowest Landau level, that's the red, and in the second Landau level we are above this ridge. This is the maximum overlap ridge. Maximum overlap with the test wave function, Parthian test wave function. The gap maximum has roughly the same slope, not exactly, but close to the same slope, slightly displaced, as you can see. But the actual message from this, maybe I should tell you what the points refer to. The points refer to the ratio between W and L naught, W the width of the wave function, standard deviation width of the wave function, divided by the magnetic length. 0, 1, 2, 3, 4. 0, 1, 2, 3 for the second Landau level. And you can see that the lowest Landau level for some system sizes, it starts in the non-quantized regime. The blue is non-quantized. This is where we saw this cliff in the previous diagram, the cliff to gapless phase, and it emerges into the gapped phase as we change the width, make the width bigger. But don't assume from this that in the thermodynamic limit we'll have a gapped phase in the lowest Landau level. I think that's probably wrong. I have a slide discussing the size dependence of this, but I don't think I have time to show this because I have 10 minutes left, and unless someone is very gracious, I won't be able to get that far. Here are the latest gap results, again, for pure Coulomb interaction, no finite width corrections. This is 8, 10, 12, 14, 16, 18, 20. It's the exciton, longest wavelength exciton that's used, plus the correction that's pulling them completely out to infinity. I mean, there is an additional Coulomb energy that you can add to pull them out to infinity. If you don't do that, there is a 1 over square root n contribution in the energy, and I wouldn't be allowed to plot it as a function of 1 over n.
So what is the temperature corresponding to this?
Pardon me?
What is the temperature corresponding to this?
The temperature? Well, that depends on density, of course. E square over L. L.
I mean, in real experiments.
In the typical experiments, okay. Are you asking for one where the fractional state occurs at 5 Tesla? That is a typical case. That value corresponds to about 3 Kelvin, or maybe even 3.5. Mind you, there are no finite width corrections, and more importantly, no lambda level mixing. If we introduce the lambda level mixing, there will be about a factor of 2 small. It will become a factor of 2 smaller. About, but again, that depends a little bit on the. That depends, of course, on the sum. So it's a bigger value than the one I had in my original paper. I think this is reasonably reliable. Well, I think the error bars are probably probably make sense.
A question about this calculation. So the gap is quite non-monotonic, right, with the system size?
Yes, it's the same at 2/5. If you look at 2/5, 1/3 has oscillations. 2/5 actually has very big oscillations as a function of system size, and you expect those oscillations because it's commensuration effects that happen. I think I'll have an illustration where they come from.
So if I add some V1 interaction in a consistent way with the system size, I know that for some other result, like the entanglement entropy, when you set the delta V1 to be close to the maximum overlap, then if you have the pure Coulomb, you have this something which is non-monotonic, and as soon as you add some delta V1, then you get a straight line. So I was wondering if for the gap I also tuned the interaction a little bit.
I have not done that.
Something.
I have not done that, but maybe you will see something that goes into this direction. An illustration of in a moment. So now I show you here the charge density of an exciton state. That's those states we use to calculate gaps. This is a 16 electron, and that's a 20 electron in lowest and second Landau level shape. Now, it's always calculated in the second Landau level, but we can look at the density profile as though these were lowest Landau level wave functions, and we can look. The reason why I do that is that in the second Landau level, everything gets very smeared out, and this smearing out hides some of these commensuration effects that I'm alluding to, if things fit on the sphere or don't fit. And it doesn't become obvious with these two yet, but it becomes obvious in what I'm going to show. So this is the quasi-particle range, where the density is too high, and this is the quasi-hole range. This is just an exciton with maximum LZ. LZ equals L. L is 8 in this case, 16 electrons, L is 8. LZ equals 8, produces a quasi-hole at the south pole, quasi-particle at the north pole. Maybe it's LZ equals -8. I'm not sure. It's either one. It's either LZ equals -8 or +8. I forgot which one it is. but of course you just flip the you just flip the. Here I show the integrated missing charge or excess charge. Excess charge is what's above the mean, and the efficiency, charge deficiency, where it's below. And you can see that the quasi-particle first time gets a quarter at about 4 magnetic length units. A plateau is barely visible. It's around 8, or in other words, when from the whole position 4 over, 4 L0. So that picture would tell us that the hole may be about 4, at least 4 magnetic length units radius. Radius would be approximately at least 4. When we look at the larger one, we again see a very similar behavior here around 4 units below the south, above the South Pole. Here is a small plateau occurring. So they are huge objects, those quasi-particles and quasi-holes. And I have, of course, I don't exactly know where to draw the line between the quasi-particle and the quasi-hole, but it looks like the quasi-hole is smaller than the quasi-particle. That would be the same actually at 1/3. 1/3 quasi-hole is much, much smaller than the quasi-particle. Whether I'm justified in dividing the space in this way, I don't make any fuss about that. But even if we use the minimum hole size, where the 1/4 charge is observed, we have a diameter of the order of 7 or 8 L0. Now I remind you that in these systems, L0 is quite a big quantity. At 4 Tesla, it would be 12 nanometers. 12 nanometers is L0. 8 L0 is 100 nanometers. It's huge. It's a huge thing. Now think that towards the edge you'll see them. This edge is going to be a tremendously wide edge. That's something that's worth bearing in mind. If in experiment one produces constrictions that are not much bigger than this, they will do harm to the quasi-particles and quasi-holes. Quasi-particle is about twice as big. So it's huge. So here I show you the density of 2 quasi-holes at North and South Pole. And I list briefly what is the problem, but I don't want to dwell on that. You have to know how to localize quasi-holes without disturbing them. You want to have just a genuine quasi-hole of 1/4 charge. You have to be very careful how you do that. In the limit where it's Pfaffian, the wave function does not have a 0 at the origin of a single quasi-hole, of a 1/4 charge quasi-hole. It only has a minimum, a local minimum. So the energy of a trapping potential that couples to density will always be finite for the single quasi-hole. For the doubly charged quasi-hole, you have a 0. So unless you do something a little bit careful, you'll see the doubly charged quasi-hole rather than the singly charged quasi-hole. It's not difficult to do right. Here I show a result for 10 electrons. That's roughly the smallest size that we. I think I have somewhere. No, that will come. That will come in a moment. We can compare this with nu equals 1/3, 2 quasi-holes at North and South Pole. Of course, in the lowest Landau level, we have exact zeros. In the second Landau level, there are no longer exact zeros. In the second Landau level image of those, they are still Laughlin quasi-holes, but now transformed into the second Landau level by raising all the wave functions from lowest to second Landau level. So that's the image of the second Landau level Laughlin quasi-hole. It doesn't have a zero, exact zero, but finite value. And you can see there is a very distinct plateau forming. The size of these is 2L0, maybe 2.3L0, the radius. It's a factor of 2 small. But, of course, L0 is also much bigger than in the Loveling case, because in the Loveling case we are at large magnetic field. So these are fairly small objects compared to the ones that I have just shown for n equals 5½ over here, there may be a slight hint at the plateau, but I think that's misleading, because if we actually go to bigger systems, we'll see that, and this is the thing I wanted to show a little bit about commensuration effects. I can change the trapping strength. This is not a delta function trapping potential, but it's extended. It's more like an electrode of finite size that's trapping the quasi-Hall. And I don't change the size, but I change the potential on this electrode, on this gate that traps the quasi-Hall. So I can actually get a much more localized quasi-Hall. You can imagine that I can make superposition of many L states so that I get a fairly localized quasi-Hall. This is less complex. But what I cannot affect is the period of the oscillations. The oscillation strength depends on how strongly I localize. And the commensuration effects come about by this bit fitting in or not fitting in. If I went to a smaller system, it would even create more damage where you want to piece them together. This is a question of the natural scale of these charge oscillations. There is a natural scale to them, and I wonder if the natural scale that you see in your calculations where you looked at the Majorana fermion properties is also of the charge nature, although at first I would not have expected it. But so this is the natural scale, and if we have a sphere of a proper size, these things will fit in very well. And the commensuration effects that we see in the energy of the exciton comes about how much misfit there is in the middle. If here we have a depression from unity in the middle. Of course, if the size of the sphere was right, there would be no depression whatsoever. It would have settled to the mean value. So it reminds us a little bit of Friedel oscillations, perhaps. If I want to more strongly bind it, I'll create larger fluctuations. Now, the other thing that comes to mind here is we again see that the 1/4 charge is observed at roughly, this is the integrated charge density degree, at around 4L0, so that's consistent with the previous calculation where we looked at the exciton. But it's huge. Radius of 8L0 is of the order of 100 nanometers. It's huge. And I have a comment how big a sphere I need to have 4 quasi-Halls. So, or 2 quasi-Halls. This analysis says to look at 4 quasi-Halls for a system of 10 electrons may be very optimistic. Very optimistic. So here I show you adiabatic continuity of ground state with 2 quasi-Halls. What do I mean? I mean the ground state, the actual ground state, the one without these what do you call them?
Quotation marks.
Quotation marks. Without quotation marks is the one where there are no defects. It's the genuine quantized state. This is the ground state that we have if we deviate with the flux by 1 unit. 1 flux more creates 2 quasi-holes. And I localize the 2 quasi-holes like I showed before on the density plots, one at the north and one at the south pole. And what do? I change the interaction from pure Pfaffian to pure Coulomb. Always with the same parameter. Lambda is never changed. It's always the lambda that fits gap in the in the large system limit. And what we see here is, first of all, this is 8 electron result. This is a 12 electron result. I can easily do also this calculation for 16 electrons. 18 is a bit on the borderline, but it could be done if one is interested. The things I want to point out is the scale here is a factor of 2 larger than here. We see here from 0 to 0.03, that's roughly the value of the gap. 0.03 would be, but we shouldn't forget that the energy scale is here also dictated by the trapping potential. The trapping potential influence on the energy scale. I have not isolated. I'm not displaying you precisely how that energy scale depends on the trapping strength. The trapping strength is the same in both cases. So the lowest energy levels, they are just nicely behaved. That's a function of x. Here we actually have a case of avoided crossing. If we look at overlaps, we'll find that the overlap is biggest across, not along the line. So it is avoided crossing. Overlap would be bigger from here to here, to the lower one, from the upper one to the lower one, and from the lower one to the upper one, than along the line. That avoided crossing is missing, is absent over here for this state. Of course, we can't label them with L because they are localized states. They are trapped. They have no L value. So that's for n equals 8 and 12. Here I show you 4 quasi-hole spectra. It's not the same thing. Now I don't trap. Spectra. L equals so and so and so and so. This is 12, this is 14. What we see is that there is more level crossing occurring here than over here, whatever that might mean. But now I show you something that we were bold. We said, well, why don't we try whether we can grade? So the simplest way of
question about the spectra.
may I do that at the end?
Okay.
So I said, well, why don't we try to grade? And actually, the first grading that we did was one that would preserve the reality of the Hamiltonian. And it's fairly difficult, and of course you have to be very symmetric in order to have a real Hamiltonian. But this one that I'm going to show you has no symmetry whatsoever. So it's a complex Hamiltonian. I wrote a complex Landschloss, and so I said, oh, the reason was that we saw something very interesting in this first attempt to grade. And when I told Bert about it, he said, well, you must look what happens when you break the symmetry, because it may be an artifact of symmetry, that you see. But it turns out it's not an artifact of symmetry. It's the generic case. So what do? We have these 2 quasi-holes on the northern hemisphere, 2 quasi-holes on the southern hemisphere. And what we do with the 2 upper ones, we twist them around by 180 degrees, thereby exchanging the position of the red and the green. I have illustrated that. Here it's about 45 degrees, and here it's fully exchanged on the right. So that the middle is an intermediate position. And this is just a case where we originally here in this left panel and in the rightmost panel, we are a little away from pure tetrahedral configuration. Those are distorted in a way, and those are distorted in a way that it looks almost like tetrahedral, but it's not. The fact that it's not can be seen that there is no mirror symmetry in the spectrum. Otherwise, if we are in a perfectly symmetric condition, then we would see symmetries in the spectrum. What typically occurs is that the two lowest levels get coupled. And there is an avoided crossing, has to be an avoided crossing, because there is no symmetry that prevents coupling. The resolution here that's needed to see that there is avoided crossing is 100 times smaller than the gap. It's a very, very small crossing, small lifting of degeneracy. And when you look at the overlap goes this way. And then, of course, this one comes over here. So you have to go twice around like on a Möbius strip to get back to where you started. And I personally think that this may be the first evidence for grading. If we do exactly the same thing at 1/3, there's no tuning actually. We didn't do any tuning, we just used something. It was a random change from a tetrahedral position. Completely unsymmetric, random change. Small change because we want to keep the distances large as possible. Of course, the distances would be largest if we were exactly in tetrahedral, but we wanted to break the symmetry because otherwise we would think, well, maybe this is a result of being too symmetric. So at nu equals 1/3, we tried to tune things and couldn't get the lowest branch and the first upper branch to somehow mix. Doesn't want to mix, whereas the one at 5/2 just automatically wanted to mix. So that's preliminary evidence for grading, I call it. Whether we can take it seriously or not, I'm just showing it. The maximum spacing in this is about 1/5 of the gap. It's less than a quarter, but it's about 1/5 of the gap. The maximum spacing between the two lowest levels. The minimum spacing, I told you, is 1/100th of the gap. And it's just a lifted degeneracy. Overlaps between states are large when crossing, not when moving along adiabatically. So it's a quasi-adiabatic. It's the same thing that Fowles and Geffen had discussed, how the 1/3 charge comes about at nu equals 1/3. And so I think Steve wants me to finish up. So this makes us hopeful. I told you which ones make us hopeful. And with this I want to close.
Any questions?
So, can you come back to my question first? So I want, if you know, the plot, not the plot, but the tendons for different sizes, 12, 14, 16, and 18, of V, so you put V Coulomb plus delta V1.
Right.
And then at delta V1 negative, the system is going to go into an L not equal to 0 state. How does this delta V1 vary with sizes? Do you know?
Yes, of course, I know something.
Or maybe I missed it. Maybe.
No, I told you that I have results that I'm not able to show. Now that you ask for them, I might just as well try to show them. I think this comes close to your question. It's not exactly the question, but it's answering something in that respect. Here I just look at the W over L naught dependence of gap for different system sizes. That's in the lowest Landau level. Not in, it's a question about whether the lowest Landau level, in the lowest Landau level, we have a chance to see path physics. This is related to the question that you're asking. It's not precisely that one. I have understood your question precisely. You want to know how far away from the boundary we are for different system sizes.
I don't even know if the Coulomb state in the thermodynamic limit is, if the delta V doesn't cross zero.
Right.
The Coulomb state is not compressible.
Right. Here I show you n equals 18 is the lowest one, n equals 16 the next one up, n equals 10, no, this is n equals, yes, this is n equals 10, and n equals 14. It's non-monotonous, what we see here. This is gap as a function of W over L naught, and if we look at the maximum gap that we observe, which is between 1 and perhaps 2 or so, in WL naught. If we always look at the maximum, we don't extrapolate to a finite value for the thermodynamic limit. That's at nu equals a half, not 5 half. At nu equals 5 half, I have no doubt that the Coulomb point is in the incompressible path radius.
If I was to keep only the 2n where n would be odd, this would be, I'm colorblind actually. So.
Yeah, so you want the 10, the 14 and the 18. Those would be the ones that only divide by 2.
Right, so would those be monotonic?
The 10, the 14, no, they are not.
Okay.
10, 14, 18.
Okay.
They are not monotonic. But I think in the second Landau level they are monotonic. The lowest Landau level is bizarre. I really don't believe that there is a quantized phase in the lowest Landau level of this kind. I think the composite fermion liquid looks fairly stable.
So I had a question about this spectrum.
Yes,
so the
I know.
evolution of the pole quadriole.
It's this one.
So this
The-
here,
Well-
you consider only the states which are adiabatically evolved from the zero
No.
energy state.
What I did was I always used the lowest 8 states.
Lowest 8 states.
The lowest 8 states. That's why we can't keep track of the ones that come down over here. They are very high excited states over here somehow. But these are the lowest 8 states that we looked at in the near path limit. It's a horrendous calculation when they are almost degenerate, and of course then we use these block launchers with many with large block size.
I may add something which is relevant to the question. So we have looked at the thermodynamic energies of the Hoppian and the composite fermion Fermi. And in the lowest Landau level, there is a substantial difference with the Fermi having lower energy, and at the second Landau level, it's the other way. But of course, this would leave out subtle, very weak here in the composite fermion. That's not.
It just seems to me that plot is a useful plot to have,
Yeah.
even for the second Landau level.
Well, I think
I-
my feeling about it is that there is no doubt that the path phase extends to the thermodynamic level. I have no, there is not a single hint that it might not be still in the path phase. Well, in a path phase, or one that still has big overlaps for these system sizes. Of course, we can't, without having established that there is no phase transition at some n equals 112, you know, we can never be 100% sure, of course. This is only a guidance. It's how seriously we take these numerical results is a question of your upbringing. If you're brought up in the domain of exact mathematics, you'll say, so what? And if you're brought up in the domain of numerical mathematicians, then they will say, can't you do much better?
Maybe we should take further questions offline, and thank you all for a nice talk.
You don't have any structure like
No, it doesn't have to be a waste of time.
No, sure, that's